Okay, we didn't record the first little part of lecture, so I wanted to review that and stick that on the front of this video of class. Here's what we've been doing. This is our endeavor. Our endeavor is, you know how fast something is changing, and you want to know how much of it you have. Here's an example of that. We've got a relationship showing the rate of change of volume of oil per day as a function of number of days since the oil started leaking. And we ask the question, what's our goal in terms of this specific situation? What are we trying to determine? So this goes back to at the top of the screen there. You know how fast something is changing. That's we're given this rate of change graph. You want to know how much of it you have. And so our goal is how much of it we have. And so what is it that we're measuring the amount of? Well, that's volume of oil, or meters cubed of oil. So we want to know the total amount of oil that's leaked out. But that's a changing amount, right? So as days go by, even hours go by, that amount is changing. So this is the idea of a function. So we want a function that outputs the total amount of oil at any number of days since the leak began. So that's the most powerful thing we could have, because then we can just pick any day since the leak started, and this function will tell us how much the total amount of oil. Okay? So remember our rate of change functions, normally we put those on the left side of the two graphs. That's our rate of change function. In this case, it's the oil leak rate at X days. And what's our goal? Our goal is the accumulation function. In this case, the total accumulation of oil at X days. So this is our unknown quantity here, how much oil has leaked out at X days. So what's the difficulty? The difficulty of this is that the rate that we're given is a continually changing rate. And the tool that we have to calculate the total amount of something is based on constant rate of change. So we need constant rate of change to know, to get amounts, to get definitive amounts of a quantity. We need constant rate. So what do? What's the approach that we take in light of this difficulty? Well, we take that rate of change function that's continually changing, and we kind of replace it or simulate it with a function made up of constant rates that pretend to be this given rate of change function. And that's the endeavor that we're on, taking a continually changing rate of change function, simulating it with a constant rate of change, piecewise constant rate of change function, in order to be able to make these calculations of total amount, in this case total amount of oil leaked into the ocean. Okay, and so this is where the class video picks up. Okay, let's go back here. Okay, so we have the rate of change of oil. Our independent quantity is days elapsed since oil started leaking. Okay, and what is the output of this function? The output of this function. Okay, so the units is meters cubed per day, and what kind of thing is that? The rate of change at which oil is leaking per day. So we know if we want to build an accumulation function, we have to use constant rates to do that. So we want to simulate this rate of change function. Okay, so we want to simulate the rate of change by using constant rates over intervals of 0.25 days. Why 0.25 days? Because I said so, okay? We could use 0.4, we could use 0.6, we could use 0.1. That's what I decided, okay? That's what I decided. So here we are in the first interval of 0.25 days. And we want to have a constant rate over this interval. What's the goal of that constant rate over that interval? What are we trying to do? We need to place a constant rate over this interval from 0 to 2.5. How? Why? What are we trying to do with that constant rate?
Pretend that there's a constant rate at that interval that we try and estimate the change, how much of it has leaked within that interval.
Okay, right. So how about here? Constant rate right here. No. How about here? How about up here? No, the point is I'm trying to match the rate function with this constant rate. I want a constant rate that's trying to pretend to be this one. Okay, so a constant rate somewhere like between 20 and 30 would be a valid way of trying to approximate some kind of constant rate between, say, 20 and 28. You see that? Meters cubed per day would be reasonable to try to match this function.
So it doesn't really matter where we take that from on the graph? As long as
No, that's the idea of it. No, but we need to be systematic. Okay, we're going to be. But what I'm saying is that in general, we're trying to have a constant rate that's trying to be close to the actual rate. That's all I'm saying.
So for each interval, though, you want to kind of take it from the same spot, though?
We're going to be systematic about it. So we need to decide here. There's different systems of choosing exactly what rate value we want for that constant rate, and here's one. Okay, so this is one. We're going to use the actual rate of change at the left side of the starting value of each interval to be the constant rate over that entire interval. So in that first interval, from 0 to 2.5, what will the value of our constant rate be if I use the actual rate at the left side or starting value of that interval? So I'm going to look at this, and I'm going to go, and I'm going to look where? The left side, and pick off that function value. And now for that whole interval from 0 to 2.5, I'm going to have that constant rate up there. Okay? And then from 2.5, okay, so here's a confusion that students have. They think of that like as a flag. Which way is the flag flying? Which way is it flying? Flying to the right. Okay? Don't think of it that way. Why? Because we use the left side of the interval to pick off the rate. So this using left doesn't mean that the flags will fly to the left. Okay? Don't think of it that way. It's not the way that the constant rates are pointing from the graph. We're using the actual rate on the left side of that interval to be the constant rate on that whole interval. So don't look at how the flags are flying and try to match that up with this. Okay? Now, let's just do the next one together, and then I'll set you loose. So from 0.25 to 0.5, what are we going to look at? What x value do we look at? We're going to look at the left side, which is 0.25, and we're going to look at the rate of change there, which is about what? 21? 21, 22, something like that. And so then, for that whole interval from 0.25 to 0.5, the constant rate of change is whatever it was at 0.25. Okay, so you guys keep going. Get help if you need help. Work together if you want. Get help if you need it. Get help. Can you just walk around? Are you doing okay? Oh, I'm sorry. If you need to leave, you can leave. Don't pick off numbers yet. We'll pick off numbers together. In terms of rates, constant rates, we'll pick those numbers off together so we're all on the same page. But you can compare to each other and to what I've done. Five. That's just 2, 3, 4, 5. Okay, anybody have a question? Okay, so let's build, we'll build the accumulation function. So according to this simulated rate of change function, what will our accumulation function be? What will its structure be like? What will its structure be like if we use this simulated rate of change to build the accumulation function? Please know this. Right, and what do we call that? That's right. Piecewise linear, right? Just like you've been working on in the last week, right? So it'll be, each one will give us a line segment in terms of building the accumulation function. So you should be able to do that, but for our purposes, we'll just do it in table form. So we'll just make a table that represents the accumulation function. That's a valid representation of a function. So we'll have, what will our input variable be for the table? Remember from our side-by-side graphs. So this is this the left graph or the right graph? This is rate of change, this is the left. Okay, so we're building a kind of a table version of the right graph. Okay, what's the input into that? Same one, right? Same input variable. And what will the output be? Total oil leaked after X days. So let's. So we don't use, so R is usually R's rate. So we could use Y. That's fine. Often we use Y to mean the accumulated amount. Okay. So at day 0 here, time 0, how much oil has leaked? 0, because we're assuming that on day 0 is when the leak begins. Okay, so then we know that after 0.25 days, how much oil has leaked after 0.25 days? We had a constant rate of change of 28, but over a quarter day, right? What is it? 7. It's going to be, so our amount of change will be our rate of change times how many days? A quarter day. So it'll be 7. So it'll be, I'm not going to, if you need to write the calculations out in your notes, write the calculations out in your notes. It's going to get messy if I do that. So do you know where the 7 comes from? Do you get where the 7 comes from? How do we calculate a change in accumulation? This is a little delta y. Delta y equals? Oh, they all said in chorus. Hey, delta x. There's a reason we did all that. We spent so long, whole module on constant rate of change. Because it's important. To get a little bit of accumulation, we take the rate. What does that rate say? It says that for every number of days that goes by, the change in oil will be 28 times as much as that. So for any number of days that goes by, the amount of oil that leaks will be 28 times the amount of days that goes by. How many days went by? A quarter of a day. Therefore, delta y was 7. And we had 0 from before. We add delta y, so the new total of y is 7. Okay. Then another quarter day later. So we'll do our delta y first. From 0.25 to 0.5 days, what was the change in y? How much oil leaked out, according to our simulated rate function? I hear nothing intelligible, but I hope you are all saying 21 times 0.25, K delta X. And what is that? 10.5? So now, what's the new total amount of accumulated oil leaked? Know where this number comes from. I did not write the calculations up. The 10.5 comes from K delta X. A rate of 21 for a quarter day, 7.5. Is that right? I'm just listening to you guys. What is it? 5.25. Thank you. I'm just listening to what I'm hearing here. So, 12.25? 12 point. Okay, I feel restlessness, I feel boredom from some of you. Not the time for either of those, okay? Here we go. 0.75. Okay, changes in y are K delta X. And where do we, so when you have a constant rate of change, the change that's computed is K times whatever the change in the independent quantity is. Okay, so what was our constant rate in the second interval? 21. That means that for any number of days that goes by, delta X, the oil output is 21 times that. K delta X. 21 times as much oil comes out as days go by. That's the rate of change. So we take 21 times 0.25. We got 5.25. We had 7 in the first quarter day, plus 5.25 more, 12.25. Okay, next, in the next quarter day, the rate of change was 15. How much did y change? 3.75? Do we have confirmation on that? So now the new total is 16 meters cubed of oil have spilled out into the ocean. We'll do one more. So after 1 day, next rate, 8. That means that for any number of days that go by, the amount of oil that comes out is 8 times the number of days. 8 times delta x. How much oil comes out in that quarter day according to our simulated function? 2. Therefore, at 1 day, our simulation of accumulation is 18, because delta y was 2. Okay, and so what would happen is our piecewise function would be linear values that connect these dots, right? Each of these would be a point on our accumulation function, and then the piecewise function would be basically lines that connect these dots. Okay, and you have lots of practice now. You could, given this rate of change function, you could make that piecewise linear function, or you should be able to. But this is another representation of that function as a table. Okay, so that's the accumulation. Back to our constant rates here, our simulated function. Simulating a changing rate of function with constant rates over intervals builds a function we call step. So that what I've drawn in blue up there, those, which looks like steps, right? It looks like steps, going down and going back up a little bit. So those blue steps is a new function, and we call that function step function. So for this example, what quantities are the input of step and the output of step? So I want you to talk to the person next to you. This is a new function, step. You better know what the input quantity is and the output quantity is. Go, talk about that. Okay. What's the input? Days. Days elapsed since oil started leaking. What's the output? Is it rate of change or is it total amount of oil? Ooh, I heard both. The step function, is it rates or is it accumulation? Rates. We're trying to simulate the rate of change function with a new function. So the input and output of step are the same as the input and output of R. The same input and output. It's just that the output, how is the output different? It's approximate. It's not exact. Okay? So the output is approximate rate of change. That's the only difference between the input and output of R and the input and output of step, is that the output is approximate values of rate of change. Okay. Any questions on what we've done in the last 5 minutes or so? Yes, sir.
When you're going from 0.25 to 0.5,
Yeah.
why would it be 6 times 0.5?
6.
Or when you have 0.5, why would it take that y value? Why would you do 21 minus 15 times your change in x minus 6? Instead of using the previous case, instead of 4 times.
I didn't think I used the previous K. I'm not understanding your question. Okay, hold on a sec. I got a question. So,
When you go from 0.25 to 0.5,
okay, so that's the second interval. He's asking about the second interval. When you go from 0.25 to 0.5.
why wouldn't you take the difference between K2 and K3 and then times that by and change next to your
No, but from 0.25 to 0.5, our approximating rate is 21. That's all that matters. That over that interval, we're assuming the rate of change. What? They all start at 0.25 increments. I just maybe drew it not so. Yeah. Does it make sense? Okay. Any other questions? Yes, sir. Yeah.
That's not going to be a step graph.
Which one? This?
Yeah, that.
Piecewise linear. These are points on our piecewise linear function, right? When it's like the basketball, right? The rocket basketball.
So those are like the right graph, right?
This is the right graph. Black is the right graph. That's we built the accumulation as a table rather than a graph. We built the accumulation function. Y is the total amount of oil, right? Our total accumulated amount. Total accumulated amount. So we're building that accumulation as a table rather than a graph. Other questions? Okay, so we want, so this is, imagine now if I said let's do intervals of 0.1. And then we're gonna build the accumulation function point by point with 1/10 of a day. How would you feel about that? A lot of work, right? So what we want, okay, too much extra conversation today. Can we get our focus to the front, please? So what we want is, we want to start employing technology to do this, all this tedious, very tedious work for us, okay? Because it's when we make those intervals smaller that what happens to our simulated rate function compared to the regular rate function? Better, right? It's very easy to see that if you make, the smaller your intervals are, the better it will approximate, but then that's a ton more work, right? Think of that process with, like I said, 1/10 of a day or even a 20th of a day. It's a lot of work, okay? So we want to start thinking about how we can get technology to do that grunt work for us, okay? All that tedious work. Okay, so here is some rate of change function. So we want to think about what are we going to need to do that. And so I posed this question. Let me make this bigger. There we go. Okay. So imagine our current value of x. Okay, this is a rate function. R of x is the output, R is the function, x is the input. So again, this is like a left-hand graph, right? This is like a graph that we see on the left. And so what I'm showing here is for delta x of 1.78, I'm showing our x continually increasing. And I'm putting your focus on, for the current value of x, I'm putting your focus on what? The x value at the left side of the current interval. So the current interval is the value of x, the current value of x is in some interval. And whatever interval it's in, we're focusing on the left x value of that interval. Why? Why are we doing that? We've got this changing rate of change function. What are we going to, yeah. Okay.
Because when you make your step function, you want to use the point to the left of the interval.
Right, so let's show a different view here. What's going to determine the rate in the current interval? What's going to determine the rate in the current interval? At the left-hand side, right. So it's going to be the rate at the x value at the left side of the interval. So that's why it's important, just like the exercise we just did. If we're going to have the computer do it for us, we've got to have a way of figuring out what that left value is, that left x value. And then the rate in that interval will be the rate at that left x value, and there'll be a constant rate the whole way. Okay, so here I am. This right here is what we usually label A, starting value of x. So A is the starting value of x.
Why did you decide to start at 0.5 instead of 0?
Because in given situations, it may start at different places. So for this one, I'm starting at 0.5, okay? So A is kind of like we think of, that's where we're going to start accumulating from. Okay, we're going to start accumulating at 0.5, and that can be different in different situations. Okay, my delta x is 1.78, so I'm going to come along here, and I'm just going to pause it. All right, so here we have some pause. We think of x increasing, but we can think about pausing x as it increases. So I want you to find this, however you can, find what that value is right there. Find exactly what that value is. If my starting value is 0.5 and my delta x is 1.78, what is the value that the finger is pointing at? That's the x value of the left side of the current interval. Find it however you can. Go. We know it's something almost like close to 6, so that's a way to check to see if you did it right. If it's something around 5.8, 5.9, then you did it right. So how do we get that x value? So someone come up, tell me your method. Somebody new. Yes, sir?
You multiply your delta x by how many intervals, because your delta x is going to be like one interval.
And how many did you find?
3 times, because there's 3 points.
He's saying there's 3 intervals, so he took 3 times the number of intervals, right? No, 3 is the number of intervals, sorry.
Yeah.
3 times the delta x.
Yeah. And then you would add your initial value of 0.5.
So he did 0.5 times 3, or sorry, 0.5 plus 3 times 1.78. And what number do you get? Let's check it, make sure it's in the ballpark. 8.4? Looks right, right? If we're looking at the graph, very close to 6. So let's generalize that. What are we doing? We're saying this is A plus, what is 3? Number of whole intervals, right? Number of whole intervals. Again, so what are we doing? We're building a formula so that we can tell technology to do this, all this hard work for us of building this step function and finding accumulation. That's why we're doing this. We need to mathematically pinpoint things so that we can tell technology what to do for us. Okay? So A plus the number of whole intervals times what? Times delta x. That should make sense. But that's going to give you, that formula right there should make sense. A plus the number of whole intervals times delta x should make sense that it will give us that right there. That x value right there. Okay, so now I'm going to switch things up. Let's make this 0.23. And let's make delta x a little smaller. I'm trying to pause with all my mic. There we go. Okay? What is A? 0.23 starting value. Anyone got the count yet? They're counting 12. And delta X is? Anyone got an answer? Looks right. 8.39. About one third of the way from 8 to 9. Does the process make sense? Not the so we got to understand that formula, not just use it. Okay, let's change it up again. I'll leave A the same. Here we go. So what is now problematic in this little kind of formula that we came up with? What's the problem, or what's the obstacle? Is A, can we get A? Yep, can we get delta X? All right, so we need a way to do this without counting manually. The computer can't count manually for us. We need to come up with a formula for this number of whole intervals so that we can just, the computer knows what we mean, okay? And we can't do it manually. And I can make it even smaller. I can make this 0.07, and you won't be able to see it all. So how are we going to get the number of whole intervals? So here's the clue. Now we need to actually use the current X, right? The current X is 8.795. And what's A? 0.23 is our starting value of A. And delta X is 0.21. How are we going to calculate the number of whole intervals from these three values? Our starting value is 0.23, our width are 0.21, and we need the one that's just to the left of when X is 8.795. How can we do this? Yes, sir?
What if you took the 8.785?
Yep. Okay, slow down. I'm gonna do this. So what are we trying to do? We're trying to get this. Ooh. Trying to get that right there. He wants to do what now? Tell me.
Take
8.795. Subtract the 0.23. And what would that represent? Okay, so for people who are trying to pay attention and if you're talking around them, they're not going to be able to, you'll be very distracted. Please don't talk. Please don't talk. So he's taking 8.795 and subtracting 0.23. What would that number represent? What is it represent? Distance, right? So it's like an interval. How wide that interval is from the starting point to our current value. Then what?
Divide whatever that value is by 0.21.
Let's measure that in chunks of, see how many chunks of 0.21 are in that width. Clever, right? You see this? You got it. We're going to take that width, starting value of A, 2x, and we're going to see how many chunks of 0.21 make up that. That'll be how many intervals. What do you get when you do that number? Someone give me a number.
40.785.
40.785. So what will this be?
40.
40. So we can take the whole length, which is x minus starting value, divide it by 0.21 to get how many chunks. But that's going to have the extra little bit that we don't want. So that would be 40. So we need a mechanism that gives us the greatest whole value less than the number we have. Okay, and what that is called the floor function. Okay, so if we put these brackets around it like this, what's inside is the 40.785, but then this says, the floor function says, just give me the whole number part. Just give me the whole number part, which is 40. So when I put those L brackets around it, we got our 40 intervals. Yes, sir?
How do you get those L brackets?
So like in graphing calculator,
Yeah.
you just type floor. You just type FLOOR, they just pop up.
Sweet.
Yeah.
Will they both pop up? Or
Yes, both of them pop up. Okay. So let's put it all together then. So it's going to be this. This is our formula for getting that left x value, right? So it's going to be a plus the whole number of intervals, which we found was the floor of, what are these here? This is x minus a over delta x. That thing is so that right there is the whole number of intervals times so given a starting value a, given a current value x and a delta x, this will calculate the x value at the left side of the current interval by doing a plus the total number of intervals times delta x. Anybody have a question? So this is a function, and we call this left. This is called, so at the output, we say left x. This is called the left function. Left of x is a plus the floor of x minus a delta x times delta x. You need to understand that formula, not just use it. So you need to know how we built it, what all the pieces mean.
when you type in left, you use
No. So, yep, graphing calculator doesn't know any function named left. You have to define it the way you define any function. It knows floor, but it does not know this function. You have to define it in just the way you define any function.
So are we making it left because we started with that left?
No, it's the left side. The x value is the left side of the current interval. Okay, remember that you do have homework for Monday. You do have homework for Monday. It's on Blackboard.